So before we start the lecture formally, let me give a brief introduction, or let me use linear algebra to actually come up with the Fourier series coefficients. So since you have already taken linear algebra, I think this will be very useful for you to see Fourier series as actually weighted sum of basis functions where the complex exponentials are the basis set. So let's use linear algebra to calculate the Fourier series coefficients. So let S of t, let S hat of t. So whenever you put a hat, this simply means this is an estimate. So this is an estimate. So S hat of t is an estimate of S of t. Okay. So S hat of t is a sum of, so this is k, goes again from minus infinity to plus infinity, sk fk of t. Okay. So these fk's are orthonormal functions. These are orthonormal functions, and this is simply the definition of a spanning set, or this is the definition of spanning actually. Orthonormal functions. Orthonormal functions. Since these are orthonormal functions, this simply means, obviously these are periodic. So over one period, fk of t, fj of t, dt equals 1 for k equals j, 0 else. Okay, so when k is equal to j, this is 1, otherwise this is 0. So this is the definition of of orthonormal functions. This is simply definition of spanning. So this is the definition of spanning. So, and these are your basis functions. So functions in the basis functions in the basis set. Okay, in the basis set. And these are obviously, if you recall from your linear algebra, this should be the projection. This should be the projection of S of t onto fk of t. So let's see whether we do get this projection or not. So then we'll see actually your Fourier series coefficients are actually projections. So let's calculate the error. So E of t is the error. So it's the error between S of t and S hat of t. Obviously, we are not interested in the minimizing the error, because this error can be both positive and negative, but we are interested in minimizing the square of the error. Okay, so minimizing, so mean square error. So mean square error. This is MSE. So we are interested in minimizing the mean square error. And this is, by the way, expectation of E of t absolute square. So this is the expectation operator. So since you have not done probability, so you don't know what's the expectation operator. So let's ignore this for a while. And just remember, this is simply equal to t and E t absolute square dt, okay, which is simply equal to t S of t minus S hat of t absolute square dt. Okay, so there's the error square and we want to minimize it. So think about, we want to minimize. So minimize mean square error. So we want to minimize the mean square error, which simply means we want to minimize this integral. So we want to minimize, S of t minus S hat of t squared dt. So if you recall from your linear algebra course, so suppose this represents your your basis function, and assume your S of t, since S hat of t is this one, So this means this is in terms in this direction. Okay, so assume that this is the plane. Assume this is the plane. So this is the plane. This is the plane. So this is the plane generated by f n t. So this is the plane generated by f n of t. And your s of t, so obviously s hat of t is here. So s hat of t is in this plane. So s hat of t is in this plane. So if s hat of t is in this plane, assume s of t is outside the plane. So s of t is outside this space. Not so s of it is in this plane, or let me call this space. There's a plane, or this is not the plane, this is space. So this is the space generated by fn of t. So s of t is outside this space. Okay. So if s of t is outside this, suppose x of t is in the room. So how do I minimize the error? So the minimum error would be if I drop a perpendicular from s of t onto this space, right? Or onto this plane. So if s of t is like this, so the minimum would be if I project this s of t onto this plane, right? If I project s of t onto this plane, this is s of t, s hat of t. So this is s hat of t, and this is simply the error. This is simply the error. So error is s of t minus s hat of t, and this, by the way, is s hat of t, right? So what I want to do is, so I want to minimize this error, and from probability theory, we know there is this orthogonality principle. We know there is this orthogonality principle. And what this orthogonality principle says is, it simply says this error is orthogonal to data. So orthogonality principle means error is orthogonal to data. This is the symbol for orthogonal. So error is orthogonal to data, which simply means your error E of t, this is the error, is orthogonal to data. And obviously data hat of t, and s hat of t is generated by fn of t. So whether we write s of hat of t or fn of t, it's one and the same thing. Is orthogonal to data, which simply means their inner product. So this is the inner product. This inner product is 0. Okay, so orthogonality implies that this is 0, and this is the definition of the inner product. So this is the definition of E of t and Fn of t. So this is the inner product. Inner, or the scalar product, if you recall from your linear algebra course, it's one and the same thing. It's the inner or scalar product of functions. Inner or scalar product. Okay, if this is true, let's plug in the values. So we have E of t is s of t into fn of t dt minus, and E of t is s hat, so goes on this side, and I get summation over here, k over here, s k f k of t, and integral here f k of t into f n of t dt, right? Where because E of t is simply s of t minus s hat of t, which is equal to s of t minus summation k s k f k of t. In general, actually, one of them has to be conjugated, but assume everything is real, so we don't need to get into those niceties. So f k of t and f n of t, this is simply equal to t when k equals, it's not equal to t, this is equal to 1. This is equal because these are orthonormal functions, or 0 else. This is because they are orthonormal functions here. So these are orthonormal functions. Because these are orthonormal functions, this is 1, otherwise it's 0. Okay, so since this is k is equal to n, so only one of the terms is left, implies only Sn remains. Only Sn remains. And this implies Sn is simply St into Fn of t dt. And what is this? This is actually the projection, or this is the inner product of S of t. This by definition, the inner product of S of t and Fn of t. And this is also the projection, which we said before. This is the projection of S of t onto Fn of t. And this is what you do when you want to find the intercept. When you want to find the intercept, for example, if you have this three-dimensional space, this is the I unit vector, this is the j unit vector, this is the k unit vector, and you want some vector in this plane. So and this vector is, suppose this is 2i plus 3j plus 4k. Then you say, okay, this 2 is the intercept along the I-axis, this 3 is the intercept along the j-axis, and this 4 is the intercept along the k-axis. Right? So this is what you, and how do you calculate this? You simply say you do x dot I, you do x dot j, x dot j, x dot j, this is 2, this is 3, and you do x dot k, this is 4. Because these are orthonormal x's, you can easily read off the value. So that is why you want to use orthonormal functions. So orthonormal function, you can simply read off the value. So this is what we have done. The same thing we have done. We have done the same thing over here. Where we have this function s of t, and we have projected s of t onto these set of orthonormal functions, and we get s of n. So s of n or s of k, since this is s of k here. So this s hat of t is the sum of the projections of s of t along these orthonormal functions f k's, right? So this is simply the projection. So if this is the projection, then this is what I said before. Okay, when you have complex functions, then you need to, the inner product is actually one of them has to be conjugate. If one of them has to be conjugate, then obviously if I put this one conjugate, I don't want to put conjugate because I'm not choose complex functions here. So maybe I'll write here this for real functions. So for real functions, this is for real functions. For complex, one of them has to be conjugate. So if we do that, obviously this will be conjugate here. And if this f of n is an exponential, if this is an exponential, then this is the definition of actually a of n, right? If this f of n, so if this is complex, if this is a complex function, then use conjugate, then use conjugate. And if this is an exponential, if this is a complex exponential, this implies your Fourier series coefficients are projections of x of t onto the complex functions, complex functions which form a basis, right? Okay. So we know that the Fourier series coefficients are projections. Now we want to see, if you recall, I said in the first lecture, your x, when you write x of t equals like this, a k e plus j k omega naught t k, I told you this is actually in the mean square sense. This is in the mean square sense. So let me see, what does this mean square sense mean? So this mean square sense simply means, okay, I want to minimize I want to minimize this energy. I want to minimize this mean square error, or this is from chapter 1, you know, this is an energy. So this is energy. So I want to minimize the energy. I want to minimize energy in error sigma, This is what I want to do. I want to minimize energy in the error signal, right? So how do I do that? So minimize energy in the error signal simply means I should use these values. I should use these values to see what is the minimum energy. Obviously, it's not going to be 0. If it's 0, then it's good enough. But if it's not 0, then I want to find the minimum energy. So what is the minimum energy? So minimum energy in error signal. This I write E min. E min is simply equal to, this is what? This should be ET absolute square dt, right? From chapter 1. This is from chapter 1. If this is true, then this should be simply E of t into E conjugate of t. E of t into E conjugate of t, or this should be equal to E of t into S hat of t, E of t into S of t dt. Why? Because E of t equals S of t minus S hat of t, and from orthogonality principle we know, which I've stated above, from orthogonality principle, E of t times Fn of t. So error and data, error is orthogonal to data. So because from orthogonality principle, Et into Fnt, so this projection is 0. So if this projection is 0, why? Because S hat of t is simply K S K F K of t. So if instead of S hat of t, I put S K F K of t, so this is Et times F K of t, so obviously this is 0. So there is no inner product between E of t and S hat of t, because they are orthogonal. So this is the one that is the non-zero thing. Okay, if this is the non-zero thing, I can write this as S square of t dt, because E of t is st minus S hat of t, minus this one, sigma k S k, because E of t is S hat of t, Sk of t F k of t S of t dt, right? This term here is S hat of t. This term here is S hat of t, and E of t is st minus S. So one st goes here. This is the S hat of t, and this is st with this one over here. So this is equal to t S square of t dt minus sigma k S k, and this is simply the projection of S of t onto Fk of t. And this should be equal to Sk, or this is, and this one is what? This is the energy in the time domain, right? Energy of S of t in time domain, right? So this is some energy of S, and this is minus K S square K. Normally this should be complex, so this should be S square S absolute of K whole square. And obviously, since this is the error, this has to be greater or equal to 0. So minimum error is this one. Okay, and if E min equals 0, so because there is an equal to sign here, this means ES equals K S square K. So this ES is the signal energy in time domain, And what is this? This is the sum of squares of spectral components. This, by the way, we'll see, this is in the past, this is the Parsifal's theorem. Sum of squares of spectral components. Okay. And when this is 0, so when this holds, so this implies, when this holds, this implies this set Fn of t is complete. This set Fn of t is complete. Okay. And how do I relate this to my Fourier series discussion? This one, what we are doing is E minimum is we are minimizing the mean square error. Since we are minimizing the mean square error, so this equality is in the mean square sense. This equality is in the mean square sense, right? So this is what it means is that you want to minimize the error. You want to minimize the error in x of t and its Fourier series representation, and that is what this equality means. This equality does not mean that for every t this holds. For every t this will not hold. This will only hold when the error is when you want to minimize the energy in the error signal. If you want to minimize the energy in the error signal, then this is what you need to do. Because this equality is not the equality in the mathematical sense that you know. This inequality is in the mean square sense, and we'll talk about mean square convergence in a little while. But before we do that, let's do the symmetry properties first. So let's do the symmetry properties first, and then we'll move on to this one. So what are the symmetry properties? So symmetry properties. So when is A naught is equal to 0? So if A naught is equal to 0, this implies 0 average value. 0 average value, or this implies signal is symmetrical across x-axis, or maybe the t-axis in your case, x-axis or the t-axis. Maybe I write to or the t-axis. Okay, or the t-axis, x-axis or the t-axis. Okay, what does zero axis symmetry mean? So zero axis symmetry implies zero axis symmetry. This is simplification in your A case, or maybe you don't have to always compute A case for every K. So zero axis symmetry implies an even signal. This implies an even signal. So even signal means what? So even signal by definition is f of t equals f of minus t. So whenever f of t is equal to f of minus t, which means this is equal to its reversed. This is the time reversed version, right? So f of minus t is the time reversed version. This is time reversed version. So if f of t is equal to this time reverse version, this simply implies only cosine terms are present. Why? Because this is an even signal, so you can't have sine, because sine is an odd function. So only cosine terms are present in the trigonometric Fourier series, in the trigonometric Fourier series representation. Okay. So these are the simplification, and these are the tests that you can see. And if you have 0 point symmetry, which means then it's an odd signal. So 0 point symmetry simply implies this is an odd signal. So even signal implies only these are present. 0 average A naught. So if the signal is symmetric around axis, this implies A naught is equal to 0. So you need no need to calculate A naught. 0 point symmetry means it's an odd signal. So odd signal implies f of t equals the negative of the time reversed version. So again, time reversed here, chapter 1. So negative of time reversed version, this simply means only sine terms are present because sine is an odd function. Sine terms are present. This is not related to the exponential Fourier series, are present in trigonometric Fourier series. Trigonometric Fourier series representation. So whenever you have odd signal, you'll always have 0 point symmetry. What about the half wave symmetry? What about the half wave symmetry? So for the half wave symmetry, we have this equation. So so this is kind of a hidden symmetry. So half wave symmetry is hidden, and I'll tell you what does hidden mean. So if your function equals the negative of the function, whether this is plus or minus doesn't make a difference. This is plus or minus doesn't make a difference. Is the negative of its if half of its version, half of its signal. So this implies no even terms, no even so maybe I say no even harmonics, no even harmonics in AK. If there are no even harmonics in AK, so what does this half wave symmetry mean? This simply means if you have a signal like this, so if you have a signal like this, and this is half is the half of this one. So this one is 0, this one is minus t by 2, right? And this is plus t by 2, this is t. So if, and this is my f of t, so hopefully they're the same length. So if this is f of t, if I take this portion and I flip it, so take this portion, flip it, and then negate it, and then I'd probably negate it. Yeah, negate is probably all right. Negate it or inverse it. Negate it. So if you flip it, this will be like this, or maybe I draw with another pen. So if you flip it, this will be like this, right? If you flip it, this will be like this. This is the same height. Sorry. So this will be like this. So when you flip it, this is like this. And when you negate it, this will be maybe, when you negate it, this will be exactly, this will, wait a minute. If this is like this, you flip it, and then I think this is not right. This is not right. If you flip it, this would be, I'm sorry. When you flip it, this would be like this. This would be like this, right? Yeah. Yeah. So if you this is flip it means you time reverse it. Flip it means time reverse it. You time reverse it. If you time reverse it, you simply flip across this axis, right? You flip across this axis. If you flip across this axis, so this would be like this. Am I right? Or this is wrong. Or maybe I'd use another function. If I flip it, this would be, no, this is not right. I'm sorry, this is not how you do it. Wait. This is not how you do it, because we have to first, we are not flipping f of t. we have to shift it first. I'm sorry. You need to shift it first. So let me go back to my function. So if this is my function, this is like this. So this is a triangle or a sawtooth waveform, and then this is like this. Okay. So this is minus t by 2, this is 0, this is plus t by 2, this is t, and this is f of t. And obviously this is a periodic signal, so goes here and goes here. Okay, so if I shift it, so let me shift it first. So let me shift it. So if I shift it to the left, so I'll get this signal. I'll get this signal over here, and I'll get this signal over here, right? And keep in mind, this is a periodic signal. So this signal, blue one, is f of t plus t by 2, right? So I can shift it on this side, I can shift it on this side, doesn't make a difference. So this is f of t by 2, and when I do minus f of t by 2, when I do minus f of t by 2, this is what I get. So when I flip it, I'll get this signal over here, and I'll get this signal over here, right? This pink one, or the purple one, is minus f of t plus t by 2. Right, and this is exactly the same as your original signal. So this holds, so no even harmonics. The easiest signal, so the easiest example is actually this one. So the easiest example is if you have this square wave. If you have this square wave, this square wave has half wave symmetry. Why? Because if this is 0, this is t by 2, this is minus t by 2. So if I shift this one, so let me again shift this one. So if I shift this one, the blue one, I will get this waveform, right? I'll get this waveform, right? I'll get this blue one. And when I get this blue one, then I flip it. Obviously, when I flip, so this blue one is actually f of t plus t by 2. Doesn't make a difference, plus or minus. And when so let me write it here. This is f of t. And when I again flip it, so when I flip this one, so again I'll get something. I'll again get something like this, right? So maybe this is not right. Right, I'll get something like this. This pink one is actually minus f of t plus t by 2. And when I say this is hidden, hidden simply means this one. Hidden means if I have this sawtooth waveform like this one. So if I have a sawtooth waveform like this one, you don't see there is this, maybe this is t, this is not t by 2. So you don't see any symmetry here, right? You don't see any symmetry here. You don't see any symmetry here, but there is a symmetry here, and that is hidden symmetry. And how do you find that hidden symmetry? You actually this waveform has some average value, and this average value is somewhere over here. This is the average value. This is the average value. If I subtract the average value, what do I get? I get exactly the waveform. So if I subtract the average value, so instead of my axis over here, instead of this axis, I'll have this axis. I'll have this axis. If I have this axis, so do you think we have hidden symmetry? You have half wave symmetry over here. Obviously, this is half. This is half now. This is half. Doesn't look like, but this is half. If I shift it by half, and then I flip it, this will be exactly like the same waveform. So you can go home and try on this one. So this is what is meant by hidden symmetry. Sometimes it's not obvious, and you have to subtract the average value and then see whether the hidden symmetry is there or not. So if you have half wave symmetry, there will be no even harmonics, and that is the case in this square wave. So in this square pulse or square wave or square pulse train, whatever you call it, so there will be no even harmonics. So A2K will be always 0. Okay. So let's talk about convergence for a little while. So why are we concerned with convergence of Fourier series? Why are we concerned about convergence of Fourier series? So convergence of Fourier series is a problem. Why? Because this sum x of t equals ak e plus j k omega naught t, k goes from minus infinity to plus infinity. This is an infinite sum. So whenever you have an infinite sum, there are always convergence issues. This is an infinite sum, so obviously implies some convergence issues. So what Fourier claimed was, so Fourier's claim that any periodic signal, so this is why his theory wasn't accepted for a long time, that any periodic signal, mostly by Laplace and his peers, that any periodic signal can be represented any periodic signal that can be represented by a Fourier series is not quite true. Because people said, so the scientists at that time, they said, how is it possible when sines and cosines are continuous signals, and when they sum up, they give rise to a discontinuous signal. So this square pulse is actually a discontinuous signal. So these are the discontinuities, right? So they were just wondering, and they were not accepting his theory, because they said, how is it possible that the continuous time signals, so you have sines and cosines, right? So you have sines and cosines, and you are saying of different frequencies, and you say they add up to a discontinuity. So they said this is not possible. So that's why his theory wasn't being accepted. So, and actually this is true. So his claim that there are any periods that can be represented by a Fourier series representation is not quite true. However, Fourier series can represent an extremely large class of periodic signals. So, and there are very few. So from an engineering point of view, there are actually almost negligible or almost zero signals that do not have a Fourier series representation. From an engineering point of view, or from an engineer's point of view, all signals do have a Fourier series representation. So let's talk about the validity. So validity of Fourier series. So validity of Fourier series representation. So consider x n of t. So these are some 2n plus 1 terms. This is what this is. K is equal to minus n plus n. A k. So we have truncated the Fourier series basically. E plus j k omega naught t. So this is a truncated Fourier series. Okay. And we find this En, which we did in the beginning of this lecture. So this is x of t minus xn of t. And we want to find, so define this one, and you find the energy, which we did, energy in En of t over one period. That is, and this is what we did, that is, we say, which we called over there E minimum over there. Actually, we minimized it. So En is simply En of t, this is chapter 1, square dt. Okay. And then I say, so, and then from the discussion in the earlier part of this lecture, we said, so this implied over there we had Sn. So now we have AKs that minimize En. Over there it was E, if you recall, that was E minimum, right? So AKs that minimize E. So I'm sorry, that was E, I think. So a case that minimize En, let me see, it was E minimum or En. So a case that minimize from the orthogonality principle, sorry. So this is the one that we are talking about, this one. So a case that minimize, and I said if the functions are complex, then you have to conjugate it. So a case that minimize En, don't want to write this one, are 1 over t x of t e minus j k omega naught t dt, right? And this is simply the projection. This is the projection. This is the projection. This is the projection of x of t onto complex exponentials, onto complex, harmonically related complex exponentials. Or maybe I say onto phi k of t. Maybe this is all right. Projection of x of t onto phi k of t, right? So this implies if x of t has a Fourier series representation, then the best approximation using only a finite, obviously we cannot do infinite, so you have to use a finite number of signals. Using only a finite number of harmonically related, only a finite number of harmonically related complex exponentials is obtained by truncating the Fourier series to desired number of terms, such that as n tends to infinity, En tends to 0. So you want to minimize the energy in the error signal. So let me define some different convergences. So uniformly convergent series. So what is a uniformly convergent series? So maybe I write it properly. So uniformly convergent series. So what is a uniformly convergent series? So a uniformly convergent series, there is arbitrary small error for all t. So for all t, there is an arbitrary small error, and we are actually looking at this one. We are looking at En of t. So we are looking at En of t, which is actually x of t minus k equals minus n to plus n, and ak e plus j k omega naught t. Yeah, so we are looking at this En. So there's arbitrary small error for all t for a finite number of terms, and this is same n. So same n for all t. Okay. And then you have pointwise convergent series. So what does the pointwise convergent series do? So for a given small error, so this is arbitrary small error, so which means almost 0. For a given small error, so a small error is permissible. For a given small error, different number of terms, so different n, different number of terms, that is n, different number of terms, that is n, guarantee convergence at different t's, So different t's, different number of terms. So pointwise convergence, different t's, different number of terms, and this is same n for all t. Same n for all t. So there's a difference between pointwise and uniformly. And then you have convergence in mean square sense. So mean square convergence. So convergence in mean square sense, and this is the one that we are interested in, mean square, convergence in mean square. Or sorry, convergence in mean square is all right. Convergence in mean square. So what is convergence in mean square? So this means the series does not converge at some t, and this is the at some t, this is the discontinuity at some t, no matter how many terms, no matter how large n is, no matter how large n is, however, energy of difference, which is ENT, energy of difference, let me write here, ENT, energy difference is ENT, energy of difference between, maybe I write it later on, energy of difference between x of t and corresponding finite term series, and this is where I write En of t, finite term series tends to 0, so tends to 0 as number of terms goes to infinity. When the number of terms goes to infinity, then this will go to a 0. So this simply means, this x of t, or maybe I write En of t dt square, or maybe no. So this implies, so it's not implies. So if x of t is a finite energy signal, if x of t is this one, so this implies finite energy signal. So if you have a finite energy signal, this will imply convergence in mean square. This will always happen. So whenever you have a finite energy signal, this will imply convergence in mean square, and this is what the equality is. So this is the equality in the Fourier series representation. Okay. So let me write this again. So one class of periodic signals, that are representable, or that can be represented by the Fourier series through Fourier series, include those that have a finite energy, over one period. 1 period. Okay, so this is what this is. So if you have an energy signal which has finite energy over one time period, then this will always converge in the mean square sense. So Dirichlet actually came up with these conditions later on, which actually are sufficient. These are sufficient but not necessary. These are sufficient but not necessary. So there may be signals that violate these conditions, but the Fourier series representations still exist. So these are sufficient but not necessary, and these imply pointwise conversion, pointwise convergence, except at discontinuity, except at discontinuity. And what is pointwise convergence, which we have already specified above. So Dirichlet's conditions imply they guarantee Fourier guarantee that x of t is equal to the Fourier series expansion. There are actually three Dirichlet's expansion for all t except where x of t is discontinuous, and at these points, Fourier series converges to average of values on either side of discontinuity, or to average of values on either side of discontinuity, This simply means if you have a signal like this, so this point here and this point here, so this will converge to this average value, right? So if this is +5, this is -5, this will be 0 volts. This is what this says, gets converged average values on either side of discontinuity. So there are three Dirichlet's conditions. The condition 1 is a weak condition. This is a weak, the other two are strong conditions. So condition 1 says over any period, x of t must be absolutely integrable, must be absolutely integrable. That is x of t absolutely integral simply means this is finite. And if this is true, so this implies ak absolute, which is equal to 1 over t absolute here minus it's not minus infinity. This is t x of t e minus j k omega naught t dt absolute. So absolute of an integral by Cauchy-Schwarz inequality is simply less than or equal to 1 over t, this one here, absolute of the integrands, and absolute of e minus j k omega naught t dt, dt is simply equal to 1 over t x of t absolute dt. This magnitude is already 1. So if this is finite, so this implies if t absolute of x of t dt is finite, this implies ak magnitude is finite, right? Okay. So there are many examples in your book. You can look at those figures because it's much easier to look at the figures instead of me drawing them. So x of t, if x of t is 1 over t for 0 less than t less than or equal to 1, this violates violates condition 1, but the Fourier series is still there. But the Fourier series still exists. So violates condition 1, but the Fourier series still exists. Okay. What about condition 2? So condition 2 is a strong condition. So condition 2 and condition 3, but they are all sufficient conditions. They are not necessary. So even if they are not met, the Fourier series will still exist. So condition 2 and condition 3 are strong conditions, and let me state them for you. Again, there are many examples in the book. You can go look at the plot, and they are actually nicer pictures than I can draw. So if any finite, so in any finite interval, in any finite interval, in any finite interval of time, in any finite interval of time, x of t is bounded, is bounded, is off bounded, is of bounded variation, is of bounded variation, is of bounded variation, implying no this. So what does bounded variation means? So bounded variation means no more than a finite number of maxima and minima, no more than a finite number of maxima and minima during any period, during any period, during any period. This means that you cannot have, you can, so within a finite number, within one period, you can not have an infinite number of maxima or minima. And one such example is this function. So if you plot this function, this has an infinite number of maximum and minima in one time period, 2 pi over t, where 0 is less than t is less than equal to 1. This violates condition 2, which has infinite maximum and minima, but it does not violate condition 1. So violates condition 2, condition 2, but not 1. Violates condition 2, but not condition 1. So if you have a signal which has an infinite number of maxima minima within one time period, the Dirichlet's conditions, they are not satisfied. Okay, so which simply means, okay, if you do x of t dt, this is 1, however has infinite number of maxima minima in one interval, in one time period. Okay. And what about condition 3? So condition 3 is also a strong one. This is related to the discontinuities, the height of the discontinuities and how many discontinuities. So condition 3 says, in any finite interval of time, in any finite interval of time, if the sum is not an infinite sum, then we do not have convergence issue. And we'll see when we do the discrete time Fourier series that we do not have any convergence issues. So in any finite interval of time, there are only a finite number of discontinuities, Moreover, each discontinuity, each of these continuities is finite. So this is a finite number of finite discontinuities. Moreover, each of these discontinuities is finite. If you have, so this simply means if you have a finite number of finite discontinuities, then it's all right. If you don't, then this is a problem. So for example, again, there's a picture in your book. Each section of a signal, each section is half the height and width of previous section. Then this will not have a finite number of finite discontinuities of previous section. So signals, so if you have a finite number of maximum minimum, or if you have a finite number of finite discontinuities, then it's all right. Then according to Dirichlet's condition, your Fourier series representation will exist. But if you don't, then there is a problem. However, signals that violate, so see this picture in your book actually, signals that violate Dirichlet's conditions do not typically arise in practical contexts. This implies convergence of Fourier series is not an issue for electrical engineers. Okay, so this is good news for you. So this also implies, thus, for a periodic signal with no discontinuities, so only the problem is when you have a discontinuity in a signal. So that's for a periodic signal with no discontinuities, Fourier series converges and equals original signal for all times with finite number of discontinuities. So this is a summary actually. So in summary, so with finite number of discontinuities, So with finite number of discontinuities, Fourier series converges everywhere. Except at discontinuities. Where, and what does it do at discontinuities? Where energy in error signal is zero, in error signal, that is En of t, is zero, or signal and Fourier series representation is same for all practical purposes. Okay. So before we end this lecture, I want to give you some tips about the phase and the amplitude spectrum. So for the amplitude spectrum, and what is the amplitude spectrum? This is AK magnitude versus K, or actually K omega naught. It's K, or actually it's K omega naught. Okay. And this says, and what are the tips? So a smooth function has less variations which simply means spectrum dies down rapidly, dies down rapidly. Okay. So if first n minus 1 derivatives, if first n minus 1 derivatives of a signal are continuous, of a signal are continuous, of a signal are continuous, and nth derivative and nth derivative is discontinuous, this implies rate of decay of AK, rate of decay of AK is 1 over k into n plus 1. So if you have a square wave, so for example, for a square wave, zeroth derivative is discontinuous, because the original signal is discontinuous. Zeroth derivative is discontinuous. This implies, and we'll see this in lecture 4, this implies AK decay as 1 over k. Why zeroth derivative? Because the square wave is like this, right? So since the square wave is like this, this is the original signal. So original signal is discontinuous. And for a triangular waveform, and a triangular waveform is smoother than the square waveform. For a triangular wave, first derivative, which is the first derivative, so the triangular waveform is like, right? So this is the triangular waveform, and the first derivative is actually is this one. The first derivative is the square wave, right? So first derivative is the square wave. So for a triangular waveform, first derivative is discontinuous, and triangular waveform is a smoother waveform than the square pulse. Square pulse is discontinuous. This implies AK decay at 1 over k square. Okay, so these are the checks, and we'll see that the Fourier coefficients of a triangle waveform die down quickly, and the Fourier coefficients of a square wave do not die down as rapidly as for the square wave, for the triangular wave. And for what happens for the phase spectrum? So in the phase spectrum is angle of AK. Phase spectrum is angle of AK versus K or K omega naught. It's K omega naught is inherent there. K or K omega naught. Okay? It's K or K omega naught. And what happens there? At a jump means at a discontinuity. At a jump, all or most harmonic components will have one sign before a discontinuity, one sign before a discontinuity, and opposite after, So this is where we want to stop today. So let's stop here, and in the next lecture we are going to look at the properties of the Fourier series. Again, if you have any questions, you can either email Dr. Babri or myself, or we can discuss it more on Mondays and Wednesdays. Thank you.